Right, hello from my side, and I will give you a quick update or the insights into the latest eruption of Ethiopia's Hayli Gubbi um, volcano that was quite lazy for the past 12,000 years. Um, and what I'm going to show here is actually the things that we observe with the MTG satellite, the newest fleet, and more particularly FCI imager and lightning imager, what did they show us, and what are the new things that I personally never seen before with the imagers in this corner of the globe. So just the first view of this true color RGB and the side view, quite relevant for later discussion. You can see there is a low-lying cloud and then the upward outburst of ash. I don't know how animations will look here, probably jumpy. Anyhow, the idea here is looking at this eruption from the dust RGB of FCI instrument. You can see very colorful the bigger number of very colorful layers of ash traveling predominantly towards the east, but in different directions altogether. We'll come to that. So predominantly eastwards, northeast, and then some of the this ash is moving northwards. And it looks like for experts in the dust RGB, it would look like a dust. It takes the same magenta shades, but the ash is actually, spectrally speaking, similar to dust, also particle size-wise, probably emission. And then we can detect it in these magenta shades that appear as a dust usually. And then there is a small cloud moving southwards. We'll come to that one. Quickly to understand the colors here. So as I said, this magenta and the reddish to orange shades, this is ash. And everything that is green to yellow and this pale blue at the end, very thin SO2 cloud, so gas. Looking at the same scene through true color RGB, so the product, at least during daytime, nighttime, is of course infrared-based dust RGB. It would look as if we would sit on the satellite. So that's the product that mimics what our eyes would see. And at the first glance, you see it is looks very natural, ash color, brownish, but not all the shades are the same, and we'll come to that. If I play it one more time, you will see that even these ash clouds, they take different shades. Right. Product that really can see the thinnest of the features in the atmosphere. If they're high up, is the cloud type from FCI, and everything that is red, it means it's very high up. And even if very thin, it's nicely picked up, like this southward moving cloud in red. So relying on near infrared 1.3 channel that can see only the high features, the red component dominates if the feature is high. If the feature is low, there's no red component. So this low level ash cloud is almost not seen. At least there is no red component to it. Comparing to Severi, so the what we had in the past, you're looking at the FCI, so MTG instrument dust RGB, and if I compare these to Severi in the next slide, you see the colors are similar. It's the same product, but the resolution definitely kicks in with the FCI, and you can see really the outlines of these clouds more nicely. How do they distribute, and where do they form, in which shape? Of course, we have the dedicated ash RGB, similar to dust RGB, but elevates a little bit this SO2 cloud. And also looking at the Severi data, just to show how still useful it is, air mass RGB that can pick up this SO2 signal in red shades. So SO2 cloud It just overlaps with the green in the ash RGB or dust RGB. So quick comparison to lower resolution instrument. Going back to a different instrument, this is lightning imager on board MTG that can detect lightning. And in this colored product, map gridded product, in different shades of yellow to red, you get the number of flashes, accumulated number of flashes, or actually this is accumulated flash area. And altogether, our internal expert Sven Erik Eno counted 37 lightning flashes from this event, separated in 265 groups. Quite intensive lightning activity for volcano, at least the first of that kind since we have this instrument on board MTG. I1 or Meteosat 12. The same thing with semi-transparent accumulations of flash overlaid over the fire temperature RGB, which gives you the hotspot. Well, probably the mouth of the volcano, where all the ash is going up. So this is a high resolution image, and I've heard the comments, and you will see it later on, that in the high resolution it almost feels like the cloud will hit your nose looking at this imagery. And it looks even more realistic if you realize that the satellite is slanted a little bit towards the east. It's at 00 lat long, so it can see this cloud going upwards from the slant angle and almost can see the trunk of the vertically developed cloud. Also because the cloud moved quickly eastwards. So it was tilted. Why do I say it? Because I got the comment from one of the human trained colleagues, Dominic Rukavina. He said, asked why the lightning is separated from the top of the cloud. Well, the blunt answer would be, most logically speaking, that most of the lightning happened actually lower in the cloud of this eruption and at the beginning of the eruption. Later on, there was no lightning activity. So with this first very strong outburst that was also responsible for the southward moving the highest ash cloud, comes the lightning, and the lightning appears to happen at the very low levels of this upward moving ash. So the separation of particles happens at the lower levels. The other possibility could be that the higher reaching cloud is optically too dense for lightning to travel through and to be detected, but yet to be investigated. This is just the first glance. Speaking of the heat signal, you're seeing here in the high speed on the right hand side. I don't know how fast in the recording will disappear, but the heat signal from the mouth of volcano seems to be very strong, and if it turns to yellow in this fire temperature RGB, that means the shorter wavelength channels manage to depict its heat, and that the heat was actually very strong in a qualitative sense. What is interesting to observe here is, aside from the heat, with this first strong outblast of ash, there is kind of shining around the lava here. If you pay good attention, maybe you notice at some point it looks like the surrounding ground is heated by something, and that something, and when I compare these two images and I think about it, that something may be just a upward or blasted lava or very hot ash in the skies that are heating a little bit the ground below it, and then this heating produces kind of a red veil, red shades around actually the lava, the hotspot in the middle. not very easily seen, but if I repeat one more time, maybe you see this red shade towards the south outlined in this orange annotation. Okay, that's something completely new, never seen before, at least I didn't see it. And the other thing I'd never seen was ash deposition. And the ash was seen, the position was seen if you compare the day before with 2 days later. And in the left, you see this comparison with the cloud phase RGB of Seviri. So 1 day before, 2 days later. I think it goes without saying, very obvious cloud on the ground of ash. So the deposited ash towards the northeast and northwest, actually, in relation to this thicker, lower laying ash cloud in magenta shades in dust RGB, if you remember. And you, on the right-hand side, you see how this looked at the ground. Confirmation from closer satellites. So the satellite on the left corner that I previously showed is 36,000, as you know. The Sentinel-2 that is shown in a high resolution here at a couple of hundreds of kilometers above, can see this darker shade towards the north, predominantly northeast, and also towards northwest. Next, I'm going to show you a couple of sandwich products. That means high resolution visible channel combined with other channels. This is typical channel infrared and the high resolution visible at 500 meters. This is where you really get the feeling that the ash cloud will hit your nose here if you come too close to the monitor, and also outlines the different levels of the ash. I'm going through a couple of RGBs combined with high resolution visible. This is dust RGB of FCI and true color at 500 meters. Now showing very nicely the shades of different levels of the clouds. Clouds traveling at a different direction have a different color. We'll come to colors. Altogether, very convincing view here from 36,000 kilometers again. Cloud phase also capable of picking up microphysics of different types of obviously ash clouds because they take different colors, but also heat signaling green here from the lava. Moving to sandwich with the already famous cloud type for its thin feature detection. Very nicely seen this southward moving thin, high thin ash cloud, and low level clouds are not so well seen. What is nice to see, especially at 500 meter, is topography over these clouds. Towards the lower sun angles, you see these wavy formations and all sorts of different, probably gravity waves happening on top of these clouds. Yeah, and the fire temperature RGB at 500 meters, also showing different colors for these clouds, meaning probably at different shades. Talking about the colors, here is really one frame zoomed in, 500 meter view of 0.6 visible channel, already some different gray shades, but if we combine this into sandwich product, we get really colors to stick up, especially because here I manually enhance the colors of each RGB or sandwich product. So dust RGB here really shows this strong green versus strong red to orange to strong magenta, different levels of ash and SO2 cloud at the different heights. Similar for the true color RGB, really different brown shades taken. Maybe this white is even sublimated water cloud at the very high tops. So ice crystals. So altogether, taking into account different shades of colors with the different shadows casted at a high resolution with the different wind trajectories of layers of this cloud, we can subjectively, in this case, count almost 10 different layers of this ash and SO2 or maybe water cloud. There wasn't much moisture, but some sublimation may happen or condensation. Anyhow, giving really the impression that you're sitting above this cloud and counting the different features moving in the different directions. Similar color depiction from the, again, cloud phase RGB, also giving all these different clouds a different colors, meaning different spectral properties, possibly different ash material. Also the height assignment, the more red, the stronger red, the brighter, the higher the feature. You can see height assignment in different colors of the cloud type RGB. And again, height from the temperature information, combining high resolution visible channel with the window infrared channel. Well, just to confirm that the in this case, fire temperature RGB has the microphysical properties and can see these different clouds in the different colors, actually, meaning probably different properties or different material. Okay, and quickly, I didn't check today where this cloud is now, but the day after, we could easily see it the morning after over Arabian Peninsula in this cloud type with the red shades, casting even shadows. That means very high up in the atmosphere. The spinning feature here is actually low-level aerosol, that's haze over Arabian Sea. Towards the end of that day, it could be seen at the edge of the FCI view, Meteosat view over the Indian subcontinent. Moving into the view of Himawari satellite, in this case, air mass RGB and the strong SO2 in red signal of the same cloud. 3 days later, you could see it still in the Himawari view in these pale green shades, the SO2 cloud separated actually in two pieces, one over Japan and one further east, or almost at the central of Pacific. And if you move your eyes to the left, you see in magenta a strong dust outbreak. By the way, just to confirm that dust may look like ash cloud if it's if the both are very low. And already towards the end of the 26th, the SO2 cloud moved to GOES view. So the American satellite geostationed the satellite positioned west in this pale green in the ash RGB. Similar as Hawaiian eruption here in parallel that happened, SO2 in green. Again, on the left, there is dust in magenta and actually tropical cyclone spinning there as well. The last thing to say and to estimate the height of this cloud, usually it goes up to the tropopause, which is maybe 10 to 15 kilometers, but there were reports that this ash cloud penetrated into stratosphere. How high? Let's see. So on the left image, you have a true color with the wind direction arrows pointing at east. So as we said, and we saw predominant eastward motion of this huge ash cloud was present, but there was some, and in this RGB, you see it in the, what is pale gray or white shades. Some of this ash cloud was moving southwards. So how come? Probably at the height where the winds were moving southwards. So if we move from 100 hectopascal, that is very high up in the stratosphere already, to only 70 hectopascal, we just moved 30 hectopascal in height. The wind direction changes dramatically, almost opposite towards southwest. So that means there is a sweet spot in between 100 and 70 hectopascal, where the wind was driving this ash cloud towards the south. And if we consult the neighboring radio sounding just across the Red Sea in the Kingdom of Saudi Arabia, we see that the wind bars move from the westward wind, or actually eastward wind, towards the south at the very top of this graph. And if we look at the numbers here of the same thing, but in numbers, there is a direction of wind, and 0 means from the north towards the south. So that's where, or 350 is also similar direction. So round about here, there was this ash cloud moving southwards, and the highest here is at 700 kilometers. So more precisely, 17 kilometers, 340 meters. That's the estimated height through this method, at least, of this ash cloud. So I'll show you some couple of nice features. If you have more questions, there was an email at the first slide, or write to training@umetsat.int, and we can take further discussions. Thank you.